Okay, so first I want to remind you of what I did yesterday. And why should I do that? It's because I want to make corrections. I did at least 2 mistakes. Preparing my talk, I realized I wrote something wrong. Okay, so what did I do yesterday? So first I proved this isolated zero principle due to Strassmann, which is effective in some sense. This, I think, was correct. Okay. Then I explained this Newton difference method and Mahler theorem for continuous functions. This was correct, except I wrote a formula which was wrong. I verified. Claudia is taking very good notes, and this was wrong. So let me do an example and explain what was wrong in my formula. So what is the example I want to do? Let's say. So let's say the first values of your polynomial function is -1, 5, like this. So this is p of 0, p of 1, p of 2, p of 3. And you know that degree of p is 3. So you have 4 values. You know that you can compute p. And for instance, you know that you can determine from this and the fact that the degree of p is 3, you know you can determine the next value, for instance. Okay? And the algorithm, what does it tell you? So you start with this sequence un here, which is 2, 6, -1, 5, etc. And you apply this difference operator. Okay, so you compute un plus 1 minus un. Right? You do it once. Okay, and then you do it again. So you -7 minus 4 is -11. 6 minus -7 is 13. 24. And then you read the coefficients here. Okay? And the formula is p of t is a sum here between from, let's say, n from 0 to 3 of coefficients an times bn of t, where bn is a nth binomial coefficient. So this formula is correct. What was not correct is what is an. An is just what you read here. Okay. This is correct. So an is what? Is you apply this differential operator n times to the sequence u, and you evaluate in 0. Okay, so that's the formula for an. And from this formula, you get this expansion Yes, this is the expansion you get. Okay. But what I wrote yesterday, you can make a correction. Here, I wrote delta n of u. But somehow I plugged an again in my formula, which is not what I wanted to. Okay, so that's the correct formula. Okay, so for instance here, you see p of t is what? Is 2 plus 4 times b1. b1 is t plus -11 times b2, which is t minus 1 over 2, plus 24 times b3. 24 times b3 is 4 times t minus 1, t minus 2. Okay? So you recover p, and then you can recover the next value. The next value is 83 if I did the computation correctly. Okay? So that's what the first correction. Then now I come back to what I want to prove, to this theorem of Bell and Poonen. one more comment. I said it yesterday, but the theorem is really due to Jason Bell, but we proved a lot of theorems. Okay? And the nice proof I will give is due to Poonen. So I like to call it Bell-Poonen theorem to remind me that this is this theorem and not another one of Bell or Poonen. So you take F, an element in the analytic endomorphism of R to the M. So R is my valuation ring, such that you can write F as the identity plus some rest, which is 0 mod a power of P. So I can write it like that, PC times G with, so you want C larger than 1 over P minus 1. Again, if C is an integer, it's just saying that it is at least 2 when P is equal to 2, or at least 1 if P is larger than 2. And G is an endomorphism of Rm. So it's just writing that F is the identity modulo P to the C, in the sense that when you reduce the coefficients mod P, you get mod P to the C, you get the identity. And then I wrote this, and I will correct it. So the statement is then there exists an analytic flow by, okay, and here I like to separate the phase space and time space, and I wrote ZP. Okay, and I said it does not extend to R here. I said that. This is completely wrong, in fact. I can put R. Okay, and I will, and the proof I will give, of course, I can put R here. But it's not really good to put R, okay? I will explain this by stating by adding a remark at the end to explain what I had in mind when I wanted to make the difference between R and ZP here. Okay. And so I will just write the formula that I want. Is that formula is phi index n. So at time n, I get the nth iterate. So that's the main thing. Okay. So I can take integral, n in n. I have an endomorphism, so I can iterate it. I get f to the n, but I can do it a priori at the beginning only for integral powers. But for this positive integral powers, I get phi index n. And as a corollary, I explained that phi is in fact in the group of Tate analytic diffeomorphisms, and phi minus 1, the inverse is, f minus 1 is phi at time minus 1. Okay? And this is what I want to prove. And the remark are the following one. This means we can take powers ft of f with t in R. Just define f power t to the t's iterate to be phi index t. Okay. This is the meaning of these things. Okay, you start with a discrete dynamics, you end up with a flow parameterized by R. But so R here is R plus an additive group. So it's also a topological group with the topology coming from the distance given by the absolute value. if R is a finite extension of ZP, if the field is a finite extension of QP, it's, this group is compact. Okay, so I put my F in an additive compact group. But the closure of the powers of F, so what I'm interested in is Fn n in N, or N in Z. Okay, and the closure of that for the topology is not R, it's just ZP in R. Okay, so this is why I want to think about ZP for the time. The natural extension for the iterates of F is more like ZP and not R. But still, so this is the mistake I made yesterday. I insisted I should not put R but ZP. In fact, I can put R. So this was my mistake. Sorry for that. Okay. And now I want to prove this theorem. Okay, so here is a picture. Okay, yeah. So this is my polydisk, and I have my transformation F. And if I start with a point Z, then I can jump to F of Z. Then F of Z. Okay, and what I'm looking for is what? I'm looking for a curve which is parameterized by R, okay, or by ZP, doing like that. Okay, and this curve will be phi index T of Z for T in R, or ZP. Okay, this is what I'm looking for. Okay, I want to interpolate this sequence of points by a curve which is analytically parameterized by T in R. And I want to do this in a way that defines globally an analytic flow when the point Z varies. Okay? So if I look at the two variables T and Z, I want something which is globally analytic. But if I just look at the orbit of one point, I have a sequence. Let's say UN is Fn of Z. Here Z is fixed. Okay? And this sequence of points, I want to interpolate it by an analytic function. Okay, this is what I was doing here, you know. I have a sequence of points, and I want to interpolate it by something which depends on some variable T. And I explained yesterday, I stated this theorem by Mahler, that if I have a sequence, if I have a continuous function or a continuous sequence in p-adic topology, I can use this formula. Now it's not a finite formula, I let n go to infinity, and this formula gives me an interpolation. And moreover, if I can control the coefficients an, and they go exponentially fast, I mean quickly, to zero, more than, when this Gauss norm, the Gauss norm of this is increasing quickly also, so you have to compensate. If I can do that in such a way that there is a compensation, then the result will be a Tate analytic power series. Okay, so we do that. Okay. So this is what I will be doing. Okay, but now you see, when I go from, I want to compute a difference like UN plus 1 minus UN. Okay, this is the difference operator applied to this sequence. What is UN plus 1 compared to UN? It's the same thing, but I have applied F. So the trick is to define a difference operator which involves f. So you define difference operator involving f as follows. You take something, h, you compose with f. This is looking at what happens step n+1 minus h. So you define this like that, okay, where h is a function, or here I will use it with an endomorphism of Rm. Okay, so I can define such an operator and look at what happens. And I will write the formulas, and it works. Okay, so I gave you exercises. Let me, I used implicitly the following statements. Let me list them. So let's say like that. Let G, H be endomorphisms of the polydisk, analytic ones, and F be a diffeomorphism of the polydisk. Then I have the following properties. So this I already explained. Where these norms are the Gauss norms. I mean, in the three properties, I'm writing Gauss norms. Okay. And I explained that using this and the fact that f is invertible, you get Gauss norm of f is 1, and G composed with f is at most G. Second property, if you compose, let me write it like this, G with identity plus H. So imagine that H is a small this is a small perturbation of the identity in Gauss norms. You want to compute the difference, then this is less than H. And the third property is this is the Gauss norm of f minus identity. So taking inverses does not change the distance to identity for diffeomorphisms. To be what? No. No. I mean, again, I take endomorphisms of Rm. In my definition, so G is given by m functions of m variables. No, you write G equal to, yes, exactly, G1, G2, Gm. So you write Gi is a sum of some coefficients, let's say ai x to the I, okay? Okay. And the Gauss norm is max of the coefficients, of these coefficients that you see, okay, for all the functions here. And my assumption is that these coefficients are in R. Okay, so the Gauss norms for the endomorphisms, they are always less than 1 or equal to 1. Okay, so here I could put the norm of G, but it's not. Okay, so this I already explained. This maybe I sketch the proof for B. You know, by linearity plus ultrametric property plus coefficients in R. You only need to do it when G is not an endomorphism, G is a function, and G is a monomial. say consider x to the I, so let's x1 to the I1, xm to the im. And then you have to plug identity. So identity m plus h is what? Is x1 plus h1 up to xm plus hm. Okay. And you plug this into this. Okay, so now G is not an endomorphism, G is just a function and this function. So G composed with identity of plus h is xy plus h1 to the I1, xm plus hm, the im. Okay. Now you just expand. Okay, so first you can choose just the xi in each parenthesis, so you get x to the I. So this is G. And then the next term I can take only, for each parenthesis I need to make a choice. So I always choose xi, except once when I choose one h. When I get like a big sum with coefficients xj and some hj. Plus some rest, okay? But let me first describe this thing. Okay. Here's the coefficient. Here what I see when I write the coefficients in power series are the coefficients of h. And all of them are less than or equal to the Gauss norm of h. Okay, so here all the coefficients are bounded from above by the Gauss norm of h. And then in the remaining terms, all the coefficients are bounded from above by the square of the Gauss norm of h, etc. So at the end, because the Gauss norm of h is at most 1, I get the inequality I want. G composed with identity plus h minus G is something less than h. Okay, so that's basically the proof of this, except that then you have to use that G is a linear combination of things like that. Okay, so now I want to prove this theorem. Okay, so I explained the strategy. I will use this difference operator and use this type of estimate. Okay. Okay, so my assumption is that f is the identity plus a small term. Okay. So I want to know what happens when I apply the difference operator to some endomorphism h. So it's h composed with f minus h. So it's h composed with identity plus p to the cg minus h. And so it's small, okay? The Gauss norm of that will be less than Gauss norm of h. I should have written that there, times Gauss norm of g times e to the minus c. Okay. Here I should have written g. It's smaller than. I'm just applying this type of things. Okay, so let me write it like that. S is 0 mod But what is important is this times p to the minus. Okay, so when I iterate, okay, so you start with this inequality and you iterate, but so you apply it once and then a second time. So here I can replace h by delta f of h, which itself is less than, okay, I have delta f of h less than p to the minus ch, then delta f square of h. So I apply this inequality with h equal to delta f of h, so I get p to the minus 2c h and so on. Okay, so delta f applied n times to h is less than p to the minus nch. So if I do it for h, which is just the identity endomorphism, it's less than p to the minus n. Okay, so this, let me write it, okay, delta f applied to identity and you evaluate on x is what? It's it's f of x minus x. And then if you apply it n times, is this sum that I wrote over there. So these endomorphisms of the unit polydisk are small in p-adic norms, okay, in the Gauss norms. So all the coefficients are small and exponentially fast in this sense. So then I define the flow as follows. Just by definition, I write this power series. So I put Bn of t, delta nf applied to identity, and I evaluate at point x. And the Gauss norm of is less than what? Something like that. Okay. And the Gauss norm of this one is smaller than p to the minus nc. So because c is larger, oh, it's big. This one is big, so it's less than that. So when I look at the product here, the Gauss norm of the product is less than p to the n over p minus 1 minus n times c. And c was supposed to be larger than p minus 1. So this is exactly the inequality I need to say that this series of functions can be written as a power series, which is a Tate analytic endomorphism. So, this formula defines a Tate analytic map from what to what? From r for the t variable times r to the m for the x variable to r to the m for the x variable. Okay, so now the proof is almost finished. I just have to explain that this formula is a good one for what I wanted. So I need to explain that it interpolates the iterates of f And I need to explain that it defines a group action of R with the addition. Okay, so I need to show that. So I need to show that. Then I will show that it is an analytic flow, so a group action of this group. And then I will deduce the second property. Okay, so first, the interpolation property. So I take n to be a non-negative integer. And I look at my formula over there. And I evaluate for t equal to n. Oh, okay, maybe n is not a good choice because my indices. Okay, I will change the indices into indices k. It's bk of n, delta k f of identity that I evaluate at the point x, k larger than or equal to 0. Okay? But here what I see are binomial coefficients, and I take their value at some integer n. And the binomial coefficients, you know, it's t minus 1 up to t minus k plus 1. So it's 0 at the first k integers. Okay? So if n is, if k is larger than n, this is 0. So this sum, in fact, is a finite sum up to n. Okay. So what is it? Now I look it like that. It's some differential, discrete differential operator applied to this endomorphism. This operator, okay, applied to this. But what is it? It's just, you know, it's a binomial coefficients. It's just k choose n. Okay? And then it's what? It's identity. The identity here is it's the linear operator, which is the identity. It's not the identity of with n, in m variable, plus delta f, iterated n times, which I apply to this endomorphism. Okay. Here, identity is the operator, linear operator on the endomorphism of the p-adic, which is just the identity operator, h goes to h. Okay? It's not the same identity as here. And delta f is just composition with f minus identity. So this is just the operator composition with f, which I iterate n times, and I apply to identity. So this is just f to the n. Okay? So I mean, the formula is made for. Okay, so I made the details clear, but it's for that we use this formula. Okay, so the interpolation is okay. So in particular, we have that phi composed n times composed with phi that you compose n prime times. Okay, f phi n composed with phi n prime is f to the n composed with f to the n prime is f n plus n prime is phi n plus n prime for integers. Okay, so we have phi s composed with phi t is phi s plus t. Okay, so meaning that s t goes to phi t is a additive homomorphism. As soon as S and T are non-negative integers. Okay. So you see, this equality is an equality of endomorphisms depending on the parameters T and S which are in R. Okay. And what I'm writing is that there is equality for an infinite number of S and T's. Okay, so by the isolated zero principle, this property must be satisfied everywhere. Okay, so you fix S to be an integer, and you compose with phi t, and you evaluate at some point z, and you know that this is equal to that for every integer t. Okay? So you make the difference. This is 0. And you write it in coordinates. So you have m analytic functions in one variable t, which vanishes when t is in capital N. So by the isolated zeros principle, this is 0 for every t now in R. Okay. And now you do it again, but you fix t, you fix z, and you let s vary, and you get it for every s in R. Okay, so this property is satisfied for all s t in R. That's the upshot of this isolated zero principle. Okay? So if it is satisfied for all choices of S and T, I can choose to evaluate this formula for S is -1 and T is 1. And what I get is phi index -1 composed with F. And this should be phi index 0, which is the identity. Okay. So phi index -1 is an inverse for F. So F is a diffeomorphism. And the inverse of F is phi at times -1. That's it. Yeah, I think I proved everything. Yes, yes, I agree. Yes, I agree. What I show is that when I write this type of equality, and I want to transfer it, from there to there, for instance, I choose a point z, I fix n, and then I apply this isolated zero principle. So I prove this equality for every z fixed. Okay. But you know, R is infinite. So when you have a power series and you know the values at infinitely many points, you can recover the coefficients. Yes, I proved this equality as an equality between functions, and I want this equality as an equality of formal power series. It works. Okay, so this is a proof of the Bell-Punnan theorem. Yes, if you want, yes. But yeah, then that was my point yesterday that I corrected at the beginning. If you do that, you get equality as functions for S and T in ZP. Because the iterates of F are, here n bar is ZP. You don't get it for S and T in R. Okay? So your argument works if you want to prove this equality for S and T in ZP, just by continuity. If you want it for S and T in R, you apply the isolated zero principle. So yes, so I'll let you write the remaining details, but all the arguments are here. Okay, so now I want to apply this theorem to the statements I gave as main goals in the introduction. Okay, so first I want to discuss this assumption. Yeah. Yes, you're right. You're right. Yes. Yes. But I don't want to discuss this. At this point, you have all the arguments, and you go back to your classical analysis textbooks with power series on fields which are uncountable. Okay. So now I want to give applications. So first, I want to comment on the theorem. You know, we have this assumption that F was supposed to be equal to the identity modulo some power of P. Okay, so in other words, I want, as an assumption to apply the theorem, I want F to be the identity plus an endomorphism. When I write it in power series, all the coefficients I see are less than P to the minus C in absolute value. Okay, small coefficients. If P is at least 3, I can take C to be 1. Okay, good. How, if I start with something which is not like that, can I replace it by something that satisfies this assumption? And what I will explain is, yes, just take a few iterates and renormalize. Okay, so I take the group of diffeomorphisms of Rm, and I will define a first subgroup, let's say D1. The subgroup of elements how to say that, F, such that F of Z is equal to Z modulo P for every Z. Okay. So let me comment on that. Okay, it's not an equality of power series. Okay? It's as a permutation of AM R mod PR. Okay. So let me remind you, if R is ZP, this is FP. Okay. So I'm looking at the action on FP points, which is the same as permutations of balls of radius, of polydiscs of radius 1 over P. Okay, so I explained yesterday, I have a homomorphism from the group of diffeomorphisms of the polydisk to the group of permutations of this finite set. Okay? And I'm looking at the kernel of this homomorphism. Okay, so it's a normal subgroup in the group of diffeomorphisms of finite index because the group of permutations of this set is finite, so the group of permutations is finite. Okay, so D1 is a finite index subgroup. The normal finite index subgroup, right? The same is true for D2, where D2 is f of z is z mod p square for every z in I don't need to write mod p square. I write this. Modulo p square, it's of z. Okay. And D2 is in D1. But let me study D1 first. So an element f in D1 fixes every point modulo p. So because it fixes the origin, I can compute the differential of f at the origin modulo p, and this gives me a homomorphism like that. I have D1. I take an element f in it. F fixes the origin, and I compute the differential of f at the origin, modulo p. So it's for the when I look at the action modulo p. So f bar is an automorphism of am over fp. It fixes the origin fp is let's say r mod pr. And I compute the differential. Okay. So I get an element in GLM of the residue field. Okay. R mod pr, right? And because all the elements in D1 fix the origin, what I get is a homomorphism. It's a little bit subtle, okay? Because first I look at the action by permutations on the points. And I define a first subgroup, which is D1, which is a normal subgroup of finite index. Now I know that all the k points of the affine space are fixed by the element of D1. Okay? So in particular, the origin is fixed. Now I look at the homomorphism I get when I reduce the coefficients of f modulo p. I get polynomial automorphisms of the affine space, because all large coefficients are 0. Okay? And I compute the differential at the origin, which is fixed. Do you have a question, Sasha? You're good? Okay, okay. Yeah, yes, you're right. That's because, okay. We discuss this after, okay? But because, yeah, yes. Okay, let's do that. And then what you get is a matrix in there, okay? And I get a homomorphism. What I want here is that this homomorphism is into a finite group again. Okay? And so now the kernel, I will define it as D. D0. Okay? D0 is the kernel of this. Okay? So these are transformations, they fix every point. okay, I made a little mistake. I explain it with, my first initial idea to define D1 was not exactly the same, and so your question did not make any sense in that case, but then I changed my mind, and then now I have somehow too many constraints on my group, but it's good, okay? So I take this kernel. So what are the elements of here? So they fix what I want. At least they fix the origin, modulo P, and the differential modulo P is just the identity map, Mi, okay. Okay, now I do the following trick. Let me state it again. An element f in D0 fixes the origin and has differential at the origin equal to identity modulo P. Okay. Okay, so when I write formulas, I can write it like this. F of x is some constant term, A0, plus some linear term, A1 of x, plus some quadratic term, A2 of x, plus blah, 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 where each term is homogeneous of degree n. Okay. So what do I mean by one term? A0 is the image of the origin. So in fact, it's a vector, okay? And A1 is a linear endomorphism. So in fact, it's given by m linear functions, okay, etc. Okay, so when I say homogeneous term of degree n, it's given by n homogeneous functions, m homogeneous functions of degree n. Okay. And what are my constraints? Constraint is A0 is 0 mod P, and A1 is the identity. Now here is the trick. You conjugate F by multiplication by P. Okay, what you get is 1 over P, F of Px. And this is 1 over P A0 plus A1, linear map commute to scalar multiplication, plus now A2, it's quadratic, so when I conjugate, there is a P square and I divide by P. So there is a P. And so on. So when I do that, let me first discuss the linear term. Modulo P, it's the identity. Good. But now let me look at the higher degree terms. Modulo P, they are all equal to 0. All the coefficients I see here are the coefficients of F, which have absolute value at most 1, because the Gauss norm is at most 1, multiplied by a positive power of P. So the Gauss norm of this is less than P to the minus 1. I'm just in trouble here. Because maybe A0 had a norm equal to P, and I divide by P, I have norm equal to 1, which is not small. But if I choose A0 to be 0 modulo P square, which means I choose F initially in D2, and I take D to be the kernel of this map, then when I renormalize, this is also 0 mod P, because this is 0 mod P square, and I divide by P. So I'm good. I mean, the hypothesis of my theorem are now satisfied. After this renormalization, F is equal to the identity when I reduced all the coefficients mod P. Okay? So this works when P is equal to 3, 5, or higher. For P equal to 2, I need to here I need to replace P by P square, and so I need to put P3 here and P square here. I mean, here it's not important. Yeah, P square here. Okay? So for P equal to 2, I need an 8 and a 4. So what did I prove? Theorem. So I define D as over there. So elements which are equal to, I mean, fixing every point modulo P square. In fact, then the differential will be the identity, but I want to insist that the differential at the origin is the identity modulo P. Okay, then, first, D is a finite index subgroup of the group of diffeomorphisms. Second, for every F in D, 1 over P F of Px satisfies the Bell-Poonen hypothesis. And so there exists a flow that interpolates 1 over P Fp. And then from this, you get that 3 for every F in D, if F has finite order, then F is the identity. Or in other words, D is torsion free. That's the statement I want to prove. So this I already explained. Okay. Why did I mix up this presentation and insisted that the derivative is at the origin is the identity when I already asked that all points are fixed mod P? It's because to do this conjugacy argument, you only need F to fix the origin and have a modulo P square and have differential equal to the identity mod P. You don't need to fix every point. So that's why I was somehow putting too many constraints. Okay. But if you just ask that the origin is fixed, So you are looking at a stabilizer of a point mod P. It's not a normal subgroup anymore. So if you want to put this finite index normal subgroup, if you want to put normal here, you need to put this. Okay. So why is it torsion free? Okay. Suppose f is given by a flow at time 1, and z in Rm is periodic for f. Then what I say is z, in fact, is fixed by f. The period is 1. I mean, yeah, 1. And again, this is a principle of isolated zeros. Proof is, so you have that f iterated k times of z is equal to z, where k is a period. Okay, but then this implies that p index k of z is equal to z. This is exactly the same map. Okay, but if you know this for k, you know it for all successive iterates. So you have this for kn. But then you write it like that, and you get m functions which are 0 on this infinite set Kn. Okay? And by the isolated zero principle, this function is 0. For every t now. And then it's 0 when t is equal to 1. So f is fixes z. Okay, so now this is an argument for periodic points, but a map, an endomorphism has order k if every points are periodic of period dividing k. So in fact, every point is fixed, so the map is the identity, both as a map and as an analytic transformation. Okay, good. Now one more comment. P equal to. Okay. Why do I need? So you know, in all this discussion, if you just work over ZP, not over a fancy extension of QP, this number C that has to be larger than 1 over P minus 1, I can just take C equal to 1. Okay. Except for P equal to, I said I need C equal to 2 at least. It's very simple. You take f of z, f of x, in one variable is minus x. Modulo 2 minus 1 is 1. Okay. So modulo 2, it is the identity. Okay. But I cannot put f in a flow because it's an order 2 element. So if I could put f in a flow, then it will be the identity by this lemma. Okay, so f is not time 1 of a flow. Okay. Okay. So to put f in a flow, I need to go to this finite index subgroup. which in fact means I need to replace f by f squared, which is the identity, of course. So I really need these finite indices. I really need C to be larger than 1 over p minus 1. If you work over extensions of QP, you can look at f of x is psi times x, where psi is root of unity, to construct this type of examples. Okay. So now I can give the applications. That is, what I have done so far is describing tools from p-adic analysis and how I can apply these tools to understand some properties of maps which are analytic diffeomorphisms of polydisks. But what I want to do is prove theorems concerning polynomial automorphisms of the affine space, for instance, or algebraic varieties. How do you do that? So there is one trick I already explained. If you have a polynomial automorphism defined with formulas over Z or ZP, then you can consider it as an endomorphism, analytic endomorphism. But the second trick is more important. Suppose you start with a polynomial automorphism with complex coefficients. Then the coefficients are complex, they are not p-adic. How do you use p-adic numbers? Okay. And there is an embedding lemma, which is the following one. So here is a lemma. So you start with a finite extension, a finitely generated extension of the field of rational numbers. I will describe this notion in a few minutes. Let S in K be a finite subset. Then the lemma tells you that there exists arbitrary large prime numbers P such that K embeds into QP by some embedding iota, with iota of S contained in fact, in the unit sphere in QP. So it's what it's set of points alpha in ZP with absolute value equal to 1. Of course, if 0 is one of the element of S, I can, if I embed K in QP, 0 must be mapped to 0, and 0 does not have modulus 1. Okay, so I need to remove 0. I will first explain how we will apply this lemma. And then I will prove, sketch the proof of the lemma in the most interesting cases. Okay. So let's say that gamma in as a group of automorphisms of the affine space of M over the complex numbers, finitely generated subgroup. Okay. So this means that gamma is given by some automorphisms. Okay, so you give yourself a finite number of automorphisms, and you look at the group generated by them inside the group of automorphisms. Okay, so that's my gamma. This is my initial data. Then to this, I add, let's say, a point Z with complex coordinates, and I add the W an algebraic subvariety. Defined by some ideal, and I take generators for them, so defined by some polynomial function equal to 0, a finite number of them. Okay, so that's my initial data. This is what appears when you want to understand this first statement. I gave the visiting times of the orbit of Z under the dynamics of something in W. And then you write all the formulas. You see, you write these equations explicitly. So you write the equation, you get some coefficients in the equation. You write the formulas for the automorphisms. So you have polynomial formulas, M times S, such polynomial functions. You list the coefficients. Okay, so you define S to be the list of all coefficients in this data. And then you define K to be the field generated by S. So it's just a field which, by definition, is finitely generated. It is generated over Q by a finite set of numbers. Then the lemma tells you you can choose an embedding of K in some QP, which maps the element of S which are not 0. I mean, I do not put 0 in my coefficients into ZP. Okay, so now assume gamma is just the group generated by one transformation F. So I just have one automorphism. Then I have a point, a subvariety, and I want to understand the values of the possible integers n such that Fn of Z is contained in W. The property Fn of Z is in W. It's something which is invariant when I apply an embedding of fields. If I apply iota to the coefficients in this type of equation, I get the same numbers n. So if I prove the theorem when for the visiting times when everything is defined over ZP instead of C, I prove it over C also. Is it clear? Yes, Alexis? Yes. I stated the lemma in the best way. Okay, so this lemma is stated like that, is stronger than saying that iota of S is contained in ZP. Because I'm saying that all non-zero numbers, I can put them on the sphere of reduced one. But the only thing I will use is that iota of S is contained in ZP. Okay, what time is it? Okay. Okay, let me comment on the lemma now. I come back to the lemma. Okay, I explain how the lemma will be used. It will be used to transfer problems which are initially stated over C or any field of characteristic 0 to problems that can be proved over ZP. Now let me comment on the lemma. What does the lemma say? So I wrote arbitrarily large P. In fact, you can replace this by a set of prime of positive density among all primes. Okay, so you look at the primes P for which you can find such an embedding. Okay, so you list all of them and you count the proportion of the primes which are good compared to the first n primes. Then, in fact, you have a positive proportion at the limit. But this, to get a positive proportion, you need something like theorems of Frobenius and Chebotarev. This I won't use. But, so now I want to explain IDs for the lemma. Yes? No? So for instance, you see, example. Okay. Let's say K is Q, S is 2/3 5 1/7. Okay. How do you prove the lemma in that case? Take P larger than 7. Okay? Okay? I think it answers your question. Okay? So I will prove the theorem by examples, the lemma by examples. Take K equal Q of I. Transcendental number. And S equal to pi. Okay. In my setting, when I want to apply it, you know, K is Q adjoint S. Okay, so I will write fields like that. Okay, what do you do? Any P works. Why? You have a transcendental number. You are looking for a transcendental number in ZP of modulus 1, of absolute value 1. A ZP, I told you, it's a Cantor set. It's not countable. For the algebraic numbers in ZP, you only have countably many of them. And so a general point of modulus 1 is transcendental. So you just use this argument. So ZP is not countable. Implies it contains transcendental numbers. You choose one of modulus 1, and you map pi to this transcendental number, you're good. So you write equation for xi. So. Okay. So now you are looking for such an embedding. Okay. K, you want to embed K in some QP. So you need to map P to an element in QP that satisfies this equation on QP. So here's a coefficient of P are, let's say, integers. Okay. So you need to find, so if such an embedding exists, then modulo P, this polynomial function will have a root, a non-trivial root modulo P, okay, in FP. And in fact, conversely, this is Hensel lemma. So this I didn't prove, okay, because I cannot prove everything for these lectures. But if you find a prime P such that this polynomial function has a simple root modulo P, then you can lift this root to QP. Okay. In fact, to ZP. Okay, and how do you prove Hensel lemma? It's a Newton method, but not the Newton difference method. The Newton method you apply when you know, this method. Okay, you have a guess for the root, and you just do the tangent line, and you iterate. Okay, so this is Hensel lemma. Okay, so the only thing I need to show is that there are arbitrarily large prime numbers P such that this polynomial function has a simple root mod P. Okay, so let's say, to simplify, I want to show that this function has roots mod P for arbitrarily large P. Forget about the simple roots. And that's an exercise. So what does it mean to have a root? Let me do the exercise. Okay. What does it mean to have a root modulo P? It means that I can find an integer, n, such that P of n is, maybe I will call it Q because I have too many P's, okay? So Q of n is 0 mod P. That's my problem. I need to find pairs where P is a prime number, n is some integer, and Q mod n is 0 mod P. That's my problem. And I want to show that for large P's, arbitrarily large, I can find such a n. Okay. If this is not the case, this means that the prime number P that divides the value of Q are just a finite set of prime numbers. So, by contradiction, we will get that there is a finite set of primes P1 up to Pk, such that Q of n is divisible only by these prime numbers. So Q of n, its decomposition into prime numbers is like that. For every n. For every n, Q of n is of this type. But you see here in this expansion, each prime is at least 2. So the possibilities for the values of such numbers, you don't have many of them. Because you know it's larger than 2 to the sum of the exponent. Okay, so the numbers that you could get below some threshold m, okay, so it's possible values less than m, it's bounded, the number of them, it's bounded by something which is logarithmic in m. On the other hand, q has some degree d, so the growth of q of n is like n to the d. Okay? And when you compare, you get a contradiction. You get something logarithmic compared to something which is like m to the 1 over d. So you get a contradiction. So this proves that, in fact, the possible divisors, prime divisors of the values of q involve arbitrarily large primes. So you have root mod p for arbitrarily large p. So you have root in zp, and this gives you the embedding you are looking for. Okay. So to prove exactly the lemma, I don't want to map C into the open unit disk. I want the image of C to have modulus 1, which is the same as saying that the root that I am constructed is not 0 modulo p, which is the same as saying that I choose p that does not devise the constant term in Q. That's it. Okay, so, and how do you prove the lemma in full generality? So this is not difficult. You write so you apply this type of IDs, and you write that K is algebraic extension of a purely transcendental expansion. Okay, so you can write it like Q of P1 up to TD, where D is a transcendental degree. And then you have an algebraic extension. So you can apply the, what's the name, primitive element so of something. Okay, so to embed K, it's not hard. Okay, but you need also simultaneously embed S. And so you also have to add some data describing S. And you apply the same type of argument. Okay, so this is how you prove the lemma. I think I should stop now. So tomorrow we will get all the fruits, you know, all the consequences using this, I mean, what we have done so far. So we did the p-adic analysis. We know that we can change complex coefficients into p-adic coefficients. And so now we can mix together all things to prove the 3 theorems I described during the first lecture. That's it. Alexis, huh? Yes, it's basically the same lemma. Yeah, the C varies, so you replace C by QP, and you add this little thing that you can control the image of some finite set. But otherwise, it's the same lemma. You use exactly the same ideas, you know, transcendental numbers, what can you do? Algebraic numbers, what can you do? Okay. Except that for C, C is algebraically closed. Here, QP is not. So I also have to choose, you know, apply this argument to choose P correctly. Yeah. And so I stated this Skolem-Mahler-Lech at the beginning theorem. At the beginning, Skolem, I think, proved the result for linear recursive sequences defined over rational numbers, like that. So if you take a linear recursive sequence, everything is over the rational numbers. And you look at the indices where this sequence un is equal to 0, then this is a finite union of arithmetic progressions. Mahler then did a larger, a more general setting. And then Lech, using this lemma, proves the general case for in characteristic 0. This type of things is not correct in characteristic P. Maybe I can just write here. It's very simple. You look at x, y, z. So I'm in dimension 3, characteristic P. And so the field is this one. And you multiply by x or by t, let's say by 1, something like that. It's just a diagonal linear transformation over this field. Okay, and you start with the point 1, 1, 1. Okay. And let's look at what happens if I iterate this map p times. So I get 1 plus t to the p, but it's 1 plus t to the p times 1. And 1 is multiplied by t to the p, and then 1 is unchanged. Okay, so when I do this at time p, I get this formula. If I do this at time p to the k, I get the same formula. Okay? And you see, for each time n equal to p to the k, x is equal to y plus z. Okay? So the times n such that fn of this starting point is contained in this hyperplane, okay, contains the power of p. But you can show that, in fact, the visiting times of 1, 1, 1 in W is this space, is equal to the power of p. It's not an arithmetic sequence. Just write the formula. I mean, t is a variable, so it's just asking when is 1 plus t to the n equal to 1 plus t to the n. Exactly when n is the power of p. So you see, for this example, you show that the visiting times are not is an infinite set that does not contain any arithmetic progression. So that's somehow it's bad news. The result does not work in characteristic P. In fact, it's somehow the opposite. There is a theorem of Derksen, maybe Derksen, yes, alone, who describes precisely what happens in characteristic P for linear recursive sequences. And the result is perfect. I mean, it's a full description, and it's effective. It's very nice.